Let us start today's work. We have gone through, we were discussing the steam compound, different parameters to control the steam, to control a power plant, to control the output for the generation, efficiency, everything. So far, we have gone through how we can control the feed water and drum level, how we can control the pressure level. Now we will see how we can control the temperature level. The objective of this generator control, steam generator or boiler plant, whatever you say, is to provide the steam flow required by turbine at a design temperature and pressure, which I have discussed earlier today, earlier days. What you are supposed to do, you are supposed to produce power by means of a steam power plant or boiler or steam generating plant, etc. And this generation is being done by a component of this total unit known as turbine, you know very well. This turbine is supposed to generate high torque, which will be used to operate electricity generators, which is coupled in different ways. There are different ways, but basic things are like this. And these are supposed to be as per a design output, means what your total plant is being designed or produced, assembled, ran to make this amount of this megawatt of power from itself, and we have to do it. And that variation is allowed, but variation can be allowed from a certain value to certain value itself. Now, this is the design temperature. We have to produce. Turbine flow is to be supplied with steam. Turbine will run by the steam by pressure of high pressure steam, which will be impinged on the blade of the turbine itself. And turbine will do this totally dependent. Turbine flow movement is totally dependent on the supply speed, supply velocity of this temperature under this high temperature, under a design temperature, under a design pressure, because these blades are moving by means of the kinetic energy, which is being converted in the nozzle from the high pressure steam and high temperature steam. That energy, pressure energy and temperature is being converted to kinetic energy in the nozzle set of nozzles, which is set accordingly and focused accordingly to the turbine blades. And these variables is the design temperature and pressure you are steam supply. These variables, these pressure and temperature variables are thus controlled by fuel firing rate, air flow rate, gas flow distribution, feed water rate, and turbine turbine valve settings. But the key measurement that describes the plant parameter are steam flow rate, feed flow rate, and steam drum level and electrical power output. So actually what we are measuring, what is the flow rate, say of steam, say of flow water, say of steam drum output level, etc. In order to do it, we have to know the temperature, steam temperature control is extremely important. An accurate control of superheating temperature is required. It's important and required for efficient power consumption. You cannot go beyond that, beyond the specified and designed temperature or maximum the range of temperature. And if it is go above it, it will unnecessarily heat up the whole setup, which will lose its power and may cause a major breakdown out to it. If it is less, less energy will be supplied. Your turbine speed will change accordingly, which will be less than the normal. There will be tripping of the whole setup, etc. Though the principal variables which we are supposed to affect here, the furnace temperature first of all. While you can revise how we are generating steam, you are creating temperature in a furnace. How we are creating? You are creating different fuels. We are totally and summarily talking about the coals. Coals may have a lot of different varieties, different ignition values, different ignition timing, etc. Different ash content. It requires different air flow from air to air. They have the temperature of, the moment duration of burning is also an extremely important thing. How quickly you can burn the flame and how quickly what will the what is the speed of entering, sending the air, velocity of entering feed air into the furnace, and what is the temperature which is supposed to be the temperature of the feed ware which will be gathered or reheated, which should be heated by the using of the temperature of the furnace somewhere. All these things are important. So furnace temperatures are supposed to be fixed within a range. So many principal variables of the furnace temperature. Next, the cleanliness. If it is too much bogged with the sand, with the ashes, ashes may not be in a solid and dry state. Maybe they're liquid or pasty or semi-liquid stage also. That creates a lot of problem to clearing. So how quickly you can clean the ashes, that's an extremely important thing. Cleanliness of the radiant pendant superheater. Pendant superheater is like this, you were told earlier. It is exactly the final temperature. It is the governor of the final temperature of the superheating thing. This is the temperature quickly you have to control, because this is from here you are feeding your boiler, your turbine system. So temperature of the gas entering the convective superheater, everything is superheated, and everything is doing by means of the huge amount of heat created in the furnace, and which is being used in various ways, but source is always the furnace itself. And the temperature of the gas is simple, finally secondary and pendant superheater, all are slightly different, maybe varies from person to person. And what is the temperature of the convective superheater is extremely important. Convective superheater should be cleanliness. All these superheaters, blades and designs are made for thorough cleanliness and quickly, or maybe during the stoppage period, maybe sometimes it is diverged, or during the low load cycle, etc. Some of them are diverged and some of them are left for maintenance. And what type of maintenance we are supposed to do? Actually, there are what we are using here, the water, which is the normal water coming from a pond, primarily from river, sometimes from the ocean even. But those water are not purified water. It is the best. It should be the best thing if we can utilize the distilled and purified water itself. But the problem is, it is first of all costly. Next of all, the production we may not be at par with the your requirement itself. So you cannot use purified water except few places where, in order to, in say pendant superheater or before that, where you have to use the purified water in a small scale, which will reduce the temperature having without making any contamination or reducing any quality of the steam itself. So the cleanliness of the convective superheater is important, because even so, after doing so many things, the tubes of the superheaters may clogged, maybe half filled with the different minerals which is coming up from the with the water and with the heat of the surroundings furnace. They are maybe reacting with each other, and they are creating a list over it, making a list over the surface of the phase itself. Now, what we are supposed to do here, then the mass flow rate of gas through the convective superheater. Generally, the heat is being transferred to the different superheaters, reheaters, everything by means of radiation. Means the portion surrounding is extremely heated, and that heat is being transferred directly to the concerned water, concerned steam, whatever it may be. But sometimes it is directly conveyed by convection or conduction and convection. Means it is not coming to the coming in contact with the flames, but it coming on contact directly with the hot gases or fumes, or gas fumes, which is coming out from the furnace itself due to this heating, etc., coming out of the furnace during the burning of the coal itself. So the mass flow rate, which is going through the different superheaters, is important, because it is taking the heat out from the outside furnace by radiation or convection. And feed water temperature and variant load of the unit. Feed water temperature is also important. Feed water is not supplied directly to the from the source to the boiler itself, but it is also being heated up to a certain temperature, so that it's all this enormous amount of heat generated in the furnace is being utilized totally to increase the efficiency of the total unit itself. So temperature is very important. These variables, next is the variation or load in the unit. You know, we have discussed throughout the day the requirement or the load acting over your particular power plant or a set of power plants or a set of total power generations of a particular state. It's also varying from time to time, from 6 o'clock in the morning to again 6 o'clock in the evening, and again for the full night. That there is a load variation of load. Generally, we have noticed that the variation is the highest, the requirement is highest from say around 9 to 4 a.m., 9 a.m. to 4 p.m. in the morning. And then after the evening, it is reduced as if all the most of the work which is being done with the power station is being done in the daytime, and it is stopped, finished and stopped, and only the time power is used for lighting only. Sometimes it may so happen your generator does not produce power for the lighting of the streets, etc., because they are being replaced by the solar cells like this. So generally, requirement is only for domestic purpose in the night. This is a concept. It is general conception, but it can definitely vary from state to state and country to country. Now, so the variation load is extremely important, and your production should vary accordingly. If the load is less, your output should be less, and load is high, your output should be high, or both are have equal problematic approach to the your unit itself. So these variables are not unrelated to the internal relationship among them, but not simple. But at least one, the effort of the load variations on superheat temperature is the most important. So there are so many variables, so all of them you cannot control, but you should find out the most important variables, the load requirement, by means of the temperature of the superheat. If by controlling the temperature of the superheater in different superheaters, we can match the output of the temperature and pressure of the steam to the requirement of the turbine itself. So that if the requirement is high, turbine will get more steam and more pressure, and requirement is less, turbine will get less steam and less pressure itself. Now, feed water temperature, a reduction in steam temperature results in loss of plant efficiency. You know, the reduction plant efficiency, for example, say the drop of 20 degrees centigrade Fahrenheit results in about 1% increase 20 degrees centigrade heat temperature, resulting 1% increase in the heat. If the temperature of the steam drops, results in 1%. This results in 1% increase the heat rate. On the other hand, the rise in temperature above the design may result in overheating and failure of superheater. So the temperature falls. This heat rate increases, it results in 1% increase in the heat rate itself. But on the other hand, if the rise in temperature, just 1 second, please. Temperature control. Steam turbine, steam turbine. A reduction in steam temperature results in loss in thermal plant efficiency. Say a drop of 20 degrees centigrade steam temperature results in about 1 increase in heat rate, means 1% increase in heat rate, but heat transmitted rate. So more heat will be transferred out. Though the total efficiency, more heat you have reduced, but temperature is reduced 20 to 20 degrees centigrade less. So 1% heat is lost. The heat rate is high, so heat rate is lost because it's not you don't need it. But temperature is high above the design. it makes results in one that results in overheating and failure of superheater itself. All the reheated tubes, turbine blades even, the temperature of the saturated steam leaving the drum corresponds to the boiler's pressure and remains uh, remains constant, yes, and remains constant of steam pressure controls are in working condition. It is the superheated, reheated responses at load changes which needed to be controlled. These are several ways of doing so. First of all, we have to control the temperature. We have to control the temperature according to requirement, and you will control it by means of the superheater itself. And how will you do it? We have to let us discuss accordingly. The combined radiation convective bilateral. Radiant and convective superheaters are arranged in series. Some of them are convective, means they may become direct contact with the fumes, may not be with the flames, but with the direct contact with the fumes, which transfer this related to the water itself. And radiant, where there is no connection of the steam, but with connected with huge amount of heat generated in the furnace. They will arrange in a series to a relatively flat final steam temperature over a wide load range. So they cannot absorb same amount of heat. They can be different. So thus, radiation heat will be maximum amount of heat transfer will be easier for radiation. So, but convective is not that high. But later, they are arranged in some way. This safety relative arrangement is the flat final steam temperature. What is the wide load range? And by taking the advantage of the opposite stream temperature response to load variation itself. This superheating and attemperation. What is that? I think that about the combined convention. So what we are doing, taking the advantage of the opposite steam temperature response to load variation. So the radiated convective superheaters are arranged in series to relatively flat final temperature. What a wide load range by taking of their opposite steam temperature, because radiant is whatever may be high is not be that high as well as they burn stones or gases, but they will transfer more heat. But radiant is also in their own way transfer supposed to be transferred in a high way. So their opposite nature should be responsible to the load variation itself. Next is de-superheating attemperation. Control by attemperature means the steam temperature is the steam temperature is being reduced by removing the energy from the steam itself. In a tabular form, a portion of steam W1, omega 1, through the omega 1 means specific weight, a certain amount of steam through the tubes from a point between the primary and secondary suborbital. So by our automatic valve diverted to a shell and tube heat exchanger whose boiled water from the drum must be circulated. So what we are having here, so this superheating attemperation means a portion of the steam taken out from a point. So there is certain drainage point, you see, where you can, if you open and you can get the steam away from it to a certain extent. This is given a primary and secondary deformation by an automatic valve diverted to a shell and sheave heat exchanger, where boiled water from the drum may be circulated. So you are taking out the steam and send the heat exchanger where the drum's boiled water can be circulated, and so that it can convert into steam there. So you are not losing the steam, but you are reducing steam to a certain extent by actuating this particular valve itself, which can be done automatically if the temperature exceeds to a certain extent. The steam gives up some of its energy to the water the steam gives up some of the energy to the water and remixes with the primary steam again before coming to the superheater itself. So the steam is reduced in temperature because it transferred to the water and again it comes back from the drum itself to the intersection between primary and secondary superheater itself. Now, uh, we have an automated valve diverted to a shell and tube heat exchanger where the steam gives up some of its energy to the water and then remix, then again, then remixes with the primary steam before entering the secondary supervisor itself. So what you see here, this is the drum itself, super air exchanger, atmospheric air exchanger. It is coming from the drum. From the drum, it is coming to the primary superheater. From superheater, it is equal to omega 2. That specific heat weight is different. It's primary superheater. Then from here, the same amount of steam is released, which is being opened by opening the valve omega 1. It goes to the another heat exchanger itself. Then this heat exchanger itself is going to the omega 1. Is coming out from here as omega 1 itself. And rest of omega 1 minus omega 2 goes to the secondary supervisor and go to the turbine itself. And here this omega 1 goes back to heat the certain amount of give the heat of the furnace itself, and again then thus saturation start by means of omega 2 itself. The drum provided with a separate drum, or from the separate drum it again supplies to the primary superheater, or it supplies to the in between the primary secondary supervisor itself. And that drum is being connected to the original drum. We can supply the heated water volume to that drum itself. And now, a spray type temperature, also called de-superheater, reduces the temperature by spraying low temperature pure water from the boiler drum, or economizer exit into the line before the primary and secondary superheater, or radiant and pendant superheaters. So what we are doing? This spray type at temperature means the reductor of temperature of the steam itself is called de-superheater. Reduces the steam superheater temperature by spraying low temperature water from boiler drum or economizer exit into the line itself between the primary and secondary superheater or radiant and pendant superheater. The spray nozzle injects water into the throat of a mixing venturi. The spray nozzle will inject the water into the throat of a mixing venturi itself, whereas the water mixed with high velocity steam in the throat vaporizes and cools the steam itself to a certain extent. So what is going on? The spray type at temperature itself, de-superheater, also named as de-superheater. The temperature by spraying low temperature water from the boiler drum or economizer exit into the line between primary and superheater, secondary superheater, or radiant and pendant superheaters. They are from the same source of water. We am taking some of it by valve and spraying into the heated steam itself, so that it reduced to a certain extent the time temperature of the drum itself. The spray nozzle injects water into the throat of a mixing ventilator. What we do here, we are sending the spray water. We are sending the spray nozzle. Injects the water into the throat of a mixing ventilator, whereas water makes instead of high velocity stream through the ventilator, steam is traveling with high velocity, and where if we inject that certain stream of regular capacity, and then it is vaporized to a certain extent and extracts the latent heat and cools the steam to a certain extent, right? Because you are spraying water in this ventilator content where it is receiving highly heated steam. If you spin the water will evaporated by this heat, but it will in that for the later heat of evaporation it will absorb from the supplied stream itself, though does resulting the temperature to a certain extent itself. The venturi and the thermal slip, a high volume, high comb slip, protect the mainstream pipe from thermal shock and by an water droplet, unvapored water droplet. So we don't need water droplets, we don't need the springs, and so we are using a thermal slip in the ventilator which is protecting the water droplets from the stream to going into the by going into the next superheater or to the turbine itself. Uh, the, hmm. The otherwise might impact on the pipe is that the water and the spray must be hmm. So no deposit scale are added in the superheater's pipes. So no, just 1 second. The water spray from the high purity, so the no deposit of any scale are added to the superheater tube, pipes and turbine blades. So I am spending this water tube, this is water jet, which are mostly pure distilled waters, which should not suppose not to produce any particular deposits on the surface itself. Now, this prescribed this superheater has been quite satisfactory in its satisfactory in service. It provides a rigid and sensitive means for temperature control by controlling the amount of spray water. Steam temperature is controlled to produce a flat temperature curve. Steam is heated from on end to end, end to end in the pipes of supervisor and cooled from N to O dash in the superheater operation itself, then heated to O2P for the secondary superheater. Steam is heated from M to N. Steam heated by regarding the amount of spray water dream temperature controlled to produce a flat temperature curve beyond the point A itself. Now, steam is heated from M to N. Is heated from M to N in the primary superheater and cooled N to O in the D superheater by spray water, then again heated to O to P in the secondary superheater itself. So the energy balance spray tube attender. No, to provide rapid and sensitive means of for temperature control by regulating the amount of spray water. Steam temperature is controlled to produce a flat temperature curve to a point beyond a point A. Steam is heated from M to N in the primary heater, cooled from N to 0, and then goes for 0 to P itself. The energy balance at a steady state, omega 1 means the specific weight, multiplied by HS1 superheated steam plus omega water into H enthalpy of superheated steam is equal to omega S omega W HS2, whereas omega S and omega W mass flow rate of steam and water, H S H W specific enthalpy of steam and water in kg. Now, if the temperature is located after the first stage superheater, this superheater located after the last stage of superheater, the steam valve temperature exceeds the maximum desired super temperature. The maximum possible superheater of steam. Steam desired temperature before the temperature, which is harmful. For example, say maximum possible temperature of steam is 560 degrees centigrade, and the desuper is after the last stage of superheater. Then at a reduced load, steam temperature may shoot up to 570, which is supposed to be brought down by water spray in 960. However, in the temperature has to be limited to 560 degrees centigrade and cannot be allowed to exceed it. On the other hand, the desuper is located before the last stage of superheat. Then the rated load with no attenuation, that the steam temperature at location should be less than minus 510 degree. Should be say 510 degree, which increases 560 degree by absorption of heat in the last stage superheater. If at a reduced load, the steam temperature at this location shoots up to 520 degree, and the water will be sprayed to bring the temperature down to 510, by which the heat absorption in the last superheater rise to 560 degrees centigrade. Before the existing steam temperature turbine, the control is being done one stage ahead, and it is a prepared practice itself. Now, what is going on here? Say at a reduced load, steam temperature may shoot up to 570. The maximum possible temperature of steam is the desired load is equal to 560 degrees centigrade, not more than that. And if the default superheater is after the last stage of heater, then at a reduced load, steam temperature may shoot up to 5 centigrade. This superheater is at last this load. From there, it will go to turbine, which is brought down by water spraying by 560. However, temperature has to be limited to 560 and cannot be allowed to exceed in another way. On the other hand, if the defuser is located before the last supervisor, then at rated load, no super temperature, then the steam temperature at location should be say around 510. So already you have to reduce it and you have to increase it to our desired load. When deep supervisor is located last stage supervisor, here at rated with no temperature, steam supervisor location will become 510, means it is before going to the last stage of superheat, it is reduced to a considerable amount. So when increased by 560, the heat is the last stage of supervisor. So at a reduced load, steam temperature at 510 degrees centigrade, which is increased to 560 degrees centigrade, and absorption of heat in the last stage supervisor itself. If at a reduced load, the steam temperature at this junction stoke up to 520 degrees centigrade, water will be sprayed through to bring the temperature down to 510, by which the heat absorption in the last rise to 560 before the existing should 10.5. So reduced load temperature at the location rose up to 520, and by which the heat absorbed in the last superheater rises to 560 degrees centigrade. So after reducing to 520, we are rising the temperature up to 560 degrees in the final temperature. So the reheater is placed after the final superheater, but before the final superheater, and its next job is to spray almost pure water to the string itself, which boils there, which means that the energy required to boiling is transferred from the water itself, so that water gets itself totally cool inside the cylinder in the pipe. Next is gas pass or damper. Now here, gas bypass or damper control. So what is the steam temperature here in spray cooling is the load. Here load is 60 here, 100 here. Here secondary SEM O2P, secondary heat and primary heat. Primary superheat, these are the secondary superheat and this is the generating power. Now, it is desired to have constant steam temperature at 3 to 11, the steam 1/4 at any time. The flow of gases uh, through a convective superheater is reduced without changing the steam flow itself. Then the final temperature will be reduced. Reduced by the gas bypassing the superheater and damper control utilizes this principle, and damper control utilizes this principle. Gas is bypass of the supervision. So that is not superheating the superheater itself, it is bypassed itself. It is then designed to have constant heat temperature at 3/4 steam flow and higher than the temperature at the 3/4 temperature at the 3/4, and this temperature is designed to give proper steam temperature at 3/4 of steam flow. It at greater steam flow, some of the flue gases are bypassed around the superheater to maintain the desired steam itself. So what we are doing, we are flow of gases through a convective superheater is reduced without changing the steam flow. Steam flow remains keeps as it is, but the gas flowing surrounding it is reduced. Then the final steam temperature will be reduced to a certain extent because convection is not working to that extent. Gas bypassing of the superheater or damper control utilizes this principle. It is desired to have constant steam temperature 3/4 of the steam gas and higher. The superheater is designed to give the proper steam temperature at 3/4 steam flow. At generator time, later time flows, some of the flue gases are to be bypassed itself around the superheater to maintain the desired steam. This is exactly the steam evaporator gas pass picture of the steam evaporator and the gas bypassing itself. Here the reheater, this is the superheater, this is the economizer, and gases are coming, and this is the control of the gas itself. Flue gases coming, covering the superheater itself and coming out, and the gases are being maintained by this thing itself by gas bypass or damper control. Gas for steam temperature control. Here the gas flow is going on, superheater and economizer, and gas flow here, you are going up, coming through it and goes there to pick quickly. Okay. So far we have finished this thing, nobody attended. I am finishing this lecture now.